In this video, we'll look at the area of robust statistics very briefly. Consider an extreme country where one dictator lives with 999 other people. The dictator earns $1 billion per year, and everybody else earns $1 per year. In such an extreme case, it is difficult to answer simple questions, such as what is the average income of a person in this country? The obvious way of doing it gives you an unreasonable amount. In other words, we could compute the mean, which means we add up all these incomes. There's one income of 1 billion and 999 income of 1, and then divide by the total number of people, which is 1,000. If you do that, you see that an average person earns $1 million per year in this country, which is an absurd number, since most of these people are in fact very, very poor. Another way of computing the average is to look at the median. What we do here is we sort the numbers, which will give an array of 1,000 numbers, 999 of them 1, and one last value of 1 billion. And then we look at the middle position. We look at the position 500. There is a 1 there, so we conclude that an average person earns $1, which is a much more reasonable outcome compared to the first one. To look at another motivating example, consider an experiment. Imagine a ship is measuring depth in the ocean. Most of the numbers are reliable, and for example, most of the numbers are between 212 and 214 meters in this example. However, there are two errors that could be caused by noise or some random events, and these two numbers are unreasonably large. If you compare the average could be off from the true value, which is somewhere around these numbers. But if you compute the median, you could get a result that is much more reliable. The rationale behind the median is that if you sort the numbers, the small numbers or the very large numbers could be due to noise, and thus there could be unreliable. However, the numbers towards the center are more reliable, and in fact the number at the very center is the most reliable one. Now the question is, how do you generalize this concept to higher dimensions? In this video, we'll look at one particular way of doing it. Consider a set of endpoints in the plane, and imagine we have a point Q. The half-space depth of Q is defined as the smallest number of points in the half-space that also contain Q. In other words, we look at all the half-spaces that are infinitely many, and among half-spaces that contain Q, we'll count how many of the points at P are also inside them, and we'll look at the half-space with the smallest possible number, and that will define the depth of Q. The main theorem that we'll prove is that given any set of endpoints in d dimensions, there is always a point with half-space depth at least n over d plus 1. And such a point is called the center point, or a center point, because it's not necessarily unique. We prove the existence of center point using Helley's theorem. We consider all half-spaces that are infinitely many, all half-spaces that contain more than n minus n over d plus 1 points. Let's call this value t. We like to look at the intersection of d plus 1 such half-spaces. Observe that each half-space, hi, excludes at most t minus 1 points. This is because each half-space contains more than n minus t points, so there are at most t minus 1 points not included into hi. So if you look at the intersection of two half-spaces, you get the following. The blue half-space contains at least n minus t points, or more than n minus t points, so there are at most t minus 1 points outside it. The gray half-space has at most t minus 1 points outside it as well. So this means if you look at the intersection of gray and blue half-space, there are at most 2 times t minus 1 points outside them. And if you continue doing that, you realize that the intersection of d minus 1 half-spaces excludes at most this many points. So in other words, there are at least n minus d plus 1 times this t minus 1 points inside the intersection of these half-spaces. Since this value is always positive, we get that this intersection is non-empty. Since the intersection of every d plus 1 half-spaces is non-empty, by Helley's theorem, it would give us that the intersection of all of these half-spaces is non-empty. Consider one point inside the intersection of all these half-spaces. We would like to claim that the half-space depth of this point is at least t. Imagine that's not the case. Imagine there is a half space that contains this red point and it has less than t points. If you look at the other side of this half space, there are more than n minus t points. But this contradicts the assumption that this red point was inside all the half spaces that contained n minus t points. And in this picture, as you can see, this point clearly is not inside this half space that has at least bigger than more than n minus t points. This proof is almost correct, except that we're missing one small detail, and that is that we apply the Haley's theorem over a set of infinitely many half spaces. But we clearly cannot do that because Haley's theorem, we only proved it for a finite set of convex objects. So in other words, we have to turn this set of infinitely many half spaces into a set of finitely many half spaces. This is in fact quite simple. For every half space, instead of considering the region above this as a convex object, we look at the convex hull of the set of points inside that half space. For the purposes of this proof, this will not make any difference because once again we can prove that the d+1 such convex hulls have a point in common, have a point from the original input in common. But this will reduce the total number of convex objects we need to consider from infinitely many to at most 2 to the n. And thus we can apply Haley's theorem. And this in fact proves the existence of a center point.